Now we are moving to identify the energy components in the energy equation. Let us recall our energy conservation equation. Total energy at cross section 1 is equal to total energy at cross section 2 plus major losses plus minor losses for a control volume. We have three significant energy terms for the energy equation when we consider the fluid flow. They are potential energy, kinetic energy, and pressure energy. Let us look at these one by one. Consider a fluid cube of delta x, delta y, and delta z. And let us try to introduce the potential energy. The energy results from doing work against the force of gravity. Therefore, we clearly need a datum to define this energy. Please refer this derivation. We can build up that the potential energy is equal to rho g z delta x delta y delta z to a delta x delta y delta z cube moved z height from the defined datum. I'm sure you might remember how it introduced to the solid. It is just mgh, but see this m changes to rho g. mg changes to rho g volume, that is delta x delta y delta z. Let's move to the kinetic energy. Kinetic energy results of doing work to accelerate a body from an arbitrary chosen reference velocity. Please follow the calculations. We can prove that the kinetic energy is given by half rho v squared delta x, delta y, and delta z to the same delta x, delta y, delta z fluid cube. Please look at the calculations and understand how this half comes into the act of the equation. Now, if we define the same to solid mechanics, it's half mv squared. Now, this m goes to rho volume in fluid mechanics. The third energy term is pressure energy. We also call this as the buoyancy energy. We usually ignore this energy type in solid mechanics. However, this is an essential section for the fluid mechanics. From buoyant force, which we have already learned, we can develop this energy. Therefore, the pressure energy is much similar to the potential energy. So, the pressure energy is rho g delta h delta x delta y delta z into h for the same cube of delta x delta y delta z. Now, let us sum up these energy terms and call the energy as the total energy. Now, total energy is equal to potential energy plus kinetic energy plus pressure energy. Let us play slightly with the mathematics and obtain the total energy per unit weight. See, total energy per unit weight. So that we will have E total energy is equal to P over rho G plus V squared over 2G plus Z. Now this is the famous Bernoulli's equation. But remember, this is this much simplified form of it. Let us apply Bernoulli's equation to two cross sections of the control volume. We should be able to work for energy conservation conservation from section 1 to section 2. P1 over rho G plus V1 squared 2G plus Z1 is equal to P2 over rho G plus V2 squared over 2G plus Z2 plus HF, that is the major loss, plus minor loss. We call this P1 over rho G to be the pressure head. Look at the units, they are in meters. V1 squared over 2G to be the velocity head. Z1 to be the elevation head. And you can see that the equation is in length units even though we present the energy. Furthermore, we call the total energy to total head when we present it using meters. We represent this using total energy line. Please refer the diagram. When we only consider the elevation and pressure, we call them to be the piezometric head and presented in hydraulic gradient line. Again, please refer the figure and understand the relationship between total energy line and the hydraulic gradient line, which is in red and green. Refer these work examples and understand the application in the environment of negligible minor losses. Starting from a pipeline, then a nozzle, then Torricelli's experiments, head tubes and pitot tubes, then the discharge measuring devices like venturi meters and orifice meters. Please note the energy equation is heavily used in flow measurements. Now let us move to the last section under the energy equation, that is finding the minor losses. Researchers have found that all minor losses can be presented as a function of velocity head. So the minor losses are kv squared over 2g. The k values for each and every cases can be found from textbooks and usually given to you in examinations. Now we looked at energy equation and identified all components of energy equation. And that concludes the session.